Good evening, everyone. Myself Sana Sheikh, a second year PhD student at IIT Bombay, and I am a teaching assistant of the NPTEL course. The course name is Symmetry, Stereochemistry and Applications, and the course instructor is Professor Anshuman Roy Chaudhary from IISER Mohali. So today I am going to take your week 8 live session. So every Monday at from 7 to 9 p.m. I am taking a live session. In these live session, I am discussing the previous year assignment question, and we are discussing the solution of these questions. So it will helpful for your current assignments. So before starting today's topic, I would like to give a brief introduction. So today we are going to discuss the reducing agent and different products done by the product formed by the reaction. So these are some reducing agents here. Here you can see that this ketone or carbonyl group is getting reduced by some reagent to alcohol. So what will happen here? We will see in brief in this table. So when it is aldehyde, when we have aldehyde starting material and it's treated with lithium aluminum hydride, then it will reduce to alcohol. Then in presence of sodium borohydride also it will give alcohol, and rana nickel palladium charcoal double H uh, all the reagent will give the alcohol as a product. Now let's talk about the ketone. So when we have ketone starting material, the ketone carbonyl group will also converted to alcohol by all the reagent which is given here: lithium aluminum hydride, sodium borohydride, rana nickel, palladium charcoal, double H. Now let's talk about the ester. So as all of know that if you have attended the lecture by Anshuman Roy Chaudhary, which is available on YouTube, so you will see that ester is reduced by only lithium aluminum hydride because it's very strong reducing agent. Lithium aluminum hydride is a very strong reducing agent. It can reduce ester also, but sodium borohydride cannot reduce esters. And same for rana nickel also, and palladium charcoal also it's not effective. But double H can reduce the ester into alcohol at particular temperature. At RT only it can reduce to alcohol. At minus 78 degree it reduces to aldehyde. So you should know these things. Now let's talk about the acid. Acid is reduced by lithium aluminum hydride to alcohol, but sodium borohydride and rana nickel palladium charcoal are not able to convert the acid to alcohol. But double H can reduce acid also at, at, at different temperature. And acid chloride also reduced by lithium aluminum hydride. Sodium borohydride also can reduce the acid chloride, but rana nickel is not effective, and palladium charcoal is also not effective. And double H can also work for acid chloride to convert it into alcohol. As you can see here, told you double H can reduce esters and acid chloride to an aldehyde at minus 78 degree temperature. So temperature matters for double H. Got it? So let's talk about the first question. First question is is there predict the product of the following reaction. So what will be the product for the following reaction? So as you can see that this cyclohexene, methyl substituted cyclohexene, is treated with HBr in presence of THF. THF is uh, sorry. THF is your solvent because you require some solvent for the reaction. So THF is tetrahydrofuran is THF here and working as a solvent, and HBr is your reagent. So what will happen in this reaction? Any guesses? Any one? Yeah. There are possibility of different products. So in first case, what will happen? Carbocation formation will take place at alpha position to the methyl group, what will happen first? This hydrogen will be abstracted by this double bond, and carbocation formation will takes place here. And the second condition is that carbocation formation can be takes place over this position, third position. So if you will see both the examples, both the possibility, both the carbocations are secondary carbocations, and secondary carbocations are have equal stability. Then after formation of carbocation, what will happen? Bromine ion will attack. So this is a SN1 type reaction, as we have discussed in previous class. All of you know that. So here what will happen? Nucleophile will attack. So nucleophile will attack on carbocation here, and it can also attack on carbocation here, which is from here. So there are two possibilities, right? Now the other two possibilities is also there, because it's a stereo center will generate here. Stereo center will generate here. So if it will attack by upside or front side, we will get beta substituted bromide ion. And if it will attack from back side, or we can say here from below the plane, then we will get alpha substituted bromide ion, alpha position, that means back side of the plane, right? Then in this condition also, by third position substitution, we will get different types of product, that is alpha and beta again. Yeah. So if bromide ion will attack from front side, then we will get beta position, bromide at beta position. And if it will attack below the plane, then we will get bromide as alpha position. So there are four possibility of the product, and all will give you a equal ratio, like 1 raised to 1 raised to 1 raised to 1. All will give equal ratio, because the stability of the carbocation will be same for all the products, and we will get two intermediates. These two are intermediates. Clear? Okay, now let's talk about the next question. Yeah, next possibility is also here. See here. These are four product possibility with 1 raised to 1 raised to 1 raised to 1. Now, the second possibility is here, that if carbocation formation is take place here at second position of the methyl group, then hydride transfer reaction will take place. Hydride transfer take place here, because the driving force for this hydride transfer is stability of carbocation. So tertiary carbocation is more stable compared to the primary and secondary carbocation. So if you will see here, this hydride will transfer over here, and we will get carbocation formation at this tri-substituted carbon atom. This stereo center will generate in this molecule, and here you can see that because it is a tertiary carbocation, it is more stable, and bromine ion will attack over here, and we will get this single product. This single product, bromine will attack from below the plane side. Now this is our major product, because the stability of carbocation is playing major role in this product, and because of stability, it will become major product. And these are minor product. These four are minor product. Got it? Hydride shift is taking place here to get the most stable carbocation. I hope all of you are clear with this example. Now let's talk about the second one. Yeah, this is the second question. So again the same reaction, but the only difference is that here we have methyl group at double bond position, and in previous case it was present at alpha position. Okay, so this is the same reaction, but only the methyl group position is changed here. You can see here, right? Okay. So what will happen again? Carbocation formation will take place as in one type reaction. So here uh, this carbon will get protonated and we will get here carbocation formation. Now because this carbocation is tertiary carbocation, so it is more stable carbocation. So the reaction will proceed through this carbocation will give a major product, and the reaction which is proceed via secondary carbocation formation will give you a minor product. As all of you know that tertiary carbocation is always more stable compared to other carbocations. So this one is minor product because their product is forming via secondary carbocation formation, and here this one is a major product. I hope all of you have learned the classes which is taken by Professor Anshuman Roy Chaudhary, which is available on YouTube. So you can see the graph here also. This is the starting material. Here is product via tertiary carbocation, and via secondary carbocation what happens? This becomes the product. So if you will see the activation energy is high for the secondary carbocation compared to tertiary carbocation. So here you can see this is the activation energy, right? And in this case here activation energy is here, right? So because of the lower activation energy, tertiary carbocation is most stable. So I hope all of you are clear in this example also. Please try to solve these examples by yourself, then it will be clear to you. Now next reaction. Yeah. So which type of reaction is this? Any guesses? This is a reduction reaction. As we have discussed earlier, this is a reduction reaction, and reduction is done by sodium borohydride. So what we have done in starting this slide, see here. Sodium borohydride can reduce ketone, correct? Ketone, it can reduce ketone, but it cannot reduce esters, right? It cannot reduce esters. So here if you see in this question, we have two functional groups which can be reduced by any reducing agent. The first one is the ester group, and the second one is ketone group. So as we have seen earlier, ester cannot be reduced by sodium borohydride. Only ketone can be reduced by sodium borohydride. So what will be the product? Yeah, secondary alcohol, and this is our stereo center. That means OH can be at alpha position also and beta also. That means front side also, as well as it can be at below side. So it will give a racemic mixture. Racemic 1:1. So this is a racemic mixture. Got it? So any guesses how this reaction is happening with this reducing agent? Anyone know the mechanism? Yeah. See here. Sodium borohydride first attack on this carbonyl carbon, and hydride transfer will takes place here. So as a nucleophile, hydride will attack over here. Now in first step we will get the addition of hydride here over here, this carbon atom, and this bond will get cleaved, and we will get O minus here. Oxygen will get minus charge. Now after getting this minus charge, as we can see that in second reaction, in second condition we have water, correct? We have water. So here water, we have here water, and this O minus will abstract the proton from this H2O water. It will abstract the proton, and because the step 2 is protonation, as I told you, it will abstract the proton, it will give you a alcohol, and NaOH will be your byproduct. Got it? I hope all of you are clear with the mechanism. So I will repeat once again. First, sodium borohydride will act as a nucleophile, and hydride will attack over this carbon atom. After getting attacked by hydride ion, this double bond will break here. This pi bond will break here, and the minus charge will come on oxygen. Then in step 2, this O minus will abstract the proton from water to get the corresponding alcohol. The second step is known as protonation, and the first step is addition. Okay. Now this is the second example. So here, this reducing agent I have not discussed here, but you can learn from the videos which is available on YouTube, and also from other books which is also available in the market. So here you can see that this is the reducing agent, lithium aluminium O butoxy hydride. So here the structure will be similar to the lithium aluminum hydride, but instead of the 3 hydride ion, here we will have a O butoxide group on instead of 3 hydride ion. So this is the reducing agent, but it is rea less reactive compared to the lithium aluminum hydride. That means the lithium aluminum hydride is very strong reducing agent, but this is a mild compared to the lithium aluminum hydride. This is a milder one. So what will happen? Because it's a milder one, it will convert the ketone into aldehyde. Ketone into aldehyde. So how this reaction is going? Anyone can tell me? Anyone? Okay, I'll tell you. The mechanism of the reaction is going through, yeah. First, what will happen? Instead of chloride, consider here ketone group. Suppose we have ketone. So what will happen? This hydride of the reducing agent will act as a nucleophile, and it will attack on this carbonyl carbon. After getting attacked by this hydride, this double bond will get reduced, and it will become O minus over here. So the O minus generation will take place after addition of hydride ion. Then this negative charge will push the electron over here, and this will break the Cl bond here. And because of the breaking of this bond, we will get the aldehyde as a product. Got it? This lone pair are pushing here, and because the double bond formation is taking place here, and to satisfy the valency of carbon atom, this group will leave over here to get the aldehyde as a product. So this is the mechanism for this reducing agent. The first step is addition of hydride, and the second step is elimination of halide. Okay. Now this is the third example for reducing agent. How you will do this reaction? So if, this is a reduction of amide. This starting material is called as amide. Why it is called as amide? Because we have here carbonyl group which is attached to the nitrogen atom, and this is a uh, sub secondary nitrogen atom, we can say, or secondary amine. So this is a amide group. So amide is reduced by lithium aluminium hydride in dry diethyl ether, which is a extreme dry condition at 0 degree, to give a corresponding amine. So how this reaction is taking place? Any guesses? So here you can see that the aluminium lithium aluminium hydride is here. So this hydride will act as a nucleophile, and it will attack at carbonyl carbon atom. It will attack on carbonyl carbon atom. After getting attacked by carbonyl hydride ion, this double bond will reduce, and we will get O minus. It will generate O minus. After generating the O minus, the aluminium hydride again, aluminium will be attacked by this O minus group here, and we will get this as a intermediate. This is the intermediate. Now what will happen? The lone pair of nitrogen will push here, and it will cleave the oxygen carbon bond. It will lone pair will push here, over here, and it will cleave the oxygen carbon bond through here, and we will get iminium ion as a intermediate. Iminium ion as a intermediate, along with the removal of this whole group, lithium aluminium hydroxide. Here we will get the whole iminium ion, and this iminium ion will further attacked by the hydride ion to give the amine, corresponding amine. So hydride will again attack over here, and this lone pair will be back on the nitrogen atom, and we will get again nitrogen over here, and corresponding amine formation will take place. So this is the mechanism for the lithium aluminium hydride reaction. First step is nucleophilic attack, then generation of iminium ion, then again a nucleophilic attack of hydride to get the amine. So this is the last reaction. So how you can solve this reaction? Anyone? As you can see that the first condition has borane and PHF. Whenever we are using PHF and ether, that means the reaction condition is very sensitive. That means it is a very dry condition. That time only we are using a PHF and ether. So it's a very dry condition. PHF is formed by uh, is dry by sodium metal. So in lab, people are putting sodium to the flask of PHF, and it turns blue. The solution turns blue to it resembles that. That means that there is no moisture present in the PHF. So it's dried very carefully in the lab. For the first condition here, we have borane in PHF. That means it's a very dry condition. So what will happen? Anyone? Yeah, borane will attack over this double bond. So how it will attack? Anyone? First tell me, it will give a Markovnikov or anti-Markovnikov product. Boron electronegativity you should know for this type of reaction. So borane is always less electronegative compared to the carbon atom. That means carbon atom is high electronegative atom in this case. So because of the high electronegativity, this borane is electrophilic and it will attack on it will get attacked by this carbon here to get the BH2 ion here. I will explain the mechanism. First, you will see here just the product formation. So here, this is the Markovnikov rule product. Markovnikov product. So why it is Markovnikov product? We will see later. Then this H2O2 will attack on other side of the BH2 group to get the product. So after attacking the H2O2, after treatment with H2O2, we will get the corresponding alcohol. So H2O2 will attack from the opposite side of the BH2 to give a corresponding alcohol. So how the mechanism is going here, we can see that first step is the oxidation step. So the second step of the hydroboration reaction is an oxidation that replaces the carbon boron bond with carbon oxygen bond. So here you can see that we have first BH2 here BH2 group, then it will be treated with H2O2. H2O2 is so hydrogen peroxide. So when it will be treated with hydrogen peroxide, how the reaction will go? First the H2O2 and NOH will react with each other to give a H2O and this NaOOH. Then after formation of this intermediate in same reaction pot, it will attack over this boron atom and it will give a intermediate like this one. So because why we are using sodium hydroxide here, because the it is a deprotonated peroxide. So deprotonated peroxide is a more nucleophilic and more reactive compared to the neutral peroxide, and the base NOH is giving the speed to the reaction. That's why here we are using NaOH. So sodium is just a counter anion, and OOH will attack over here to give the this intermediate. After getting this intermediate, this here you can see that rearrangement is taking place. So rearrangement is taking place by breaking of this boron carbon bond, and after breaking of this boron carbon bond, this carbon oxygen bond formation is taking place, and the driving force for this rearrangement is cleavage of the weak oxygen oxygen bond, because oxygen oxygen bonds are weak. They are homoatomic molecule, same electronegativity, so the bond is weak. So after breaking this bond, this rearrangement is taking place, and we are getting this as a intermediate. After getting the intermediate, what will happen? This oxygen boron bond will break, because this hydroxy group will attack over BH2 group, and this oxygen boron bond will be break here, and we will get a O minus intermediate of uh, corresponding substrate, and the counter anion sodium will stabilize this O minus group. So here we will get the removal of BH2 group. Then in our reaction H2O is present. H2O is present water. So water will hydrogen of the water, that is proton, will be attacked by this O minus group to get the corresponding alcohol. So here we will get the product. So alkoxide, what will do alkoxide here? It will remove a proton from water to generate a neutral alcohol. So we will get here alcohol formation by H2O. So I hope all of you are clear here. So we will see the product here. This is the major product we will get here. Okay. Now let's revise the today's class. We have in this today's live session we have discussed the different reducing agent which are used for reduction of carbonyl group. So the first reducing agent was our lithium aluminium hydride, which can reduce the aldehyde, ketone, esters, acid chloride, all the different types of carbonyl groups, because lithium aluminium hydride is a very good reducing agent, and it has a highest nucleophilicity compared to the other reducing agent. So that's why it will reduce the aldehyde, ketone, esters, acid chloride. Now we have discussed the sodium borohydride. So as we can see in this table, sodium borohydride can reduce the aldehyde. It can also reduce the ketone, but it cannot reduce the acid and esters. Acid and esters cannot be reduced by sodium borohydride, whereas the acid chloride can also be reduced by sodium borohydride, because it's a good reducing agent, but not say not good as a lithium borohydride. Lithium aluminium, sorry, sodium borohydride is a good reducing agent, but not as good as lithium aluminium hydride. It's a weak reducing agent compared to the lithium aluminium hydride. Yeah, this is the case here. Now let's talk about the Rane nickel. As all of you know that Rane nickel can reduce the aldehyde, it can also reduce the ketone, but it cannot reduce the ester, acid or acid chloride group. So the only aldehyde and ketone can be reduced by Rani nickel. So it's already a mild reducing agent. All of you know that. Now the palladium charcoal is given here. So palladium charcoal can reduce the aldehyde. It can also reduce the ketone, but again it cannot effective for the reaction of ester acid and acid chloride. But the palladium charcoal can reduce the double bond. I hope all of you know this. Palladium charcoal can reduce the double bond. Okay, it can reduce the double bond or triple bond. But palladium charcoal is ineffective for the ester acid and acid chloride reaction. Now let's talk about the diabyl H. Diabyl H can reduce aldehyde, ketone, esters, acid chloride, but at particular temperature, that is at RT or high temperature. But at -78 degree temperature, the diabyl H will reduce ester and acid chloride to an aldehyde Okay. Then we have discussed the reactions. Today we have discussed the sixth reaction. The very first reaction was this cyclohexene methyl substituted cyclohexene reaction, which was treated with HBr in dry THF condition. As the condition is dry THF, so how this reaction will happen? Here the proton will be extracted by this carbon atom, and here carbocation formation will take place. So there are possibility of generating two types of carbocation. One is at this position, and the second carbocation can form at this position. Both are possible here. So here you can see that we will get the secondary carbocation formation in both the cases. Here also it's a secondary carbocation, and here also it's a secondary carbocation. Why it's a secondary carbocation? Because it attached to a two different substituents. The carbon atom which is attached to the two different substituents are known as secondary carbocation, or two substituent we can say. Here we have hydrogen, one hydrogen, correct? Now because the secondary carbocation are both have same equal stability, so the bromine ion will attack on the second this carbocation. So if it will attack on the first carbocation form here, so we will get 1 2 1 bromo 2 methyl cyclohexane. Then if it will attack at the third position where the carbocation formation is taking place, then we will get the 1 3 1 bromo 3 methyl cyclohexane. So this is the two possibility, but there is one more possibility was here, that is if it will attack from back side, we will get this product, this trans product. This is trans 1 bromo 2 methyl cyclohexane. And if it will attack from the front side, that is the side where the methyl group is present, we will get the cis product, correct? Here also at third position also, if it will attack from the back side, we will get the trans 1 bromo 3 methyl cyclohexane. But if it will attack from the front side, we will get the cis 1 bromo 3 methyl cyclohexane. Okay. So these are the four possibility by secondary carbocation generation or formation. Here one more possibility is there, that is the formation of tertiary carbocation. How it can be possible? This hydride can be transferred to the here at this carbocation to generate the tertiary carbocation. This is also known as a hydrogen shift or hydride shift. We can say hydride shift. So here you will see that after the hydride shift, this hydride ion will shift here. The carbocation will generate over here at this center, and this center is tertiary substituted, tri-substituted. That's why this carbocation is a tertiary carbocation. This is the tertiary carbocation. Correct? So as we have discussed earlier, tertiary carbocation have a high stability compared to secondary carbocation. So tertiary carbocation are more stable. That's why it will give this product, which is a major product. Among all the 5 products, this is the major product. Okay, major product. So we will get here 5 products. How many products? 5 products. And the major product is only this one. Why here we don't have the other isomer like here cis trans? Because methyl group is present at wedge position, that is the at front side, so the bromine ion can attack only from the back side. Only one side will be available for the bromine ion. Only one possibility is there. There is no other possibility. You can think about it by imagine this molecule, and you will see that here only one possibility is there. That's why it's a major product. So here total 5 products. Now this is the same example compared to the previous one, and the only difference was here was the methyl group substitution, or the numbering of this methyl group was present at different position. So here it is present at the carbon atom which has double bond. So the reaction condition again is same. It is HBr in dry THF. So again the carbocation formation will take place. So here we will see here, if carbocation will generate over here, we will get the tertiary carbocation formation, and if it will generate at this position, we will get the secondary carbocation. So which one is stable? We have discussed many times. Which carbocation is stable? This tertiary carbocation is more stable. This tertiary carbocation is more stable. Because of the stability, this tertiary carbocation intermediate will give a major product. So this will be our major product, and the minor product will be formed by the formation of secondary carbocation. Okay. Any other possibility? Can you guess any other products form in this reaction? No, right? Here you can see the other possibility also. Which one will be the other possibility? Sorry. The cis trans. Correct? We have discussed earlier cis trans. We can get either cis or trans. That is racemic. We will get the racemic product by secondary carbocation formation. Yeah. One possibility is this one. Correct? Cis transformation will be takes place here. But the major product will be this one only. Because here only one possibility is there. There is no cis trans possibility present. So we will get the major product here by generation of tertiary carbocation. Clear? Now this was the third reaction we have discussed in this reaction. So as we have discussed many times, the sodium borohydride can only reduce the ketone, not the ester group. Ester group will remain unaffected. So the product which we will get by reduction of sodium borohydride will be our secondary alcohol product by keeping ester group as it is or unaffected. So here we will get the stereo center. Stereo center will generate over here. So it can give a both the racemic mixture. So this product will be racemic. It can be either front side or back side. So the product will be racemic enantiomers. Two enantiomer will form here. Okay. And if we will talk about the mechanism, I will again explain here. So hydride ion from sodium borohydride will attack on this carbonyl carbon atom, and the reduction of this carbon oxygen bond will takes place, and the double bond will break here, and negative charge will generate at oxygen atom. Then this negative O minus ion will abstract the proton from water to give the OH group over here. So the first step is called as a addition of hydride group, and then the second step is called as protonation, which is done by O minus O negative ion along with the NOH as a side product. So this is the reaction, which is this is the mechanism of the reaction which is taking place in this case. Okay. So now let's see here. This is again the reducing agent, but it's a mild reducing agent compared to the lithium aluminium hydride. That's why it can only convert the ketone to aldehyde, or acid chloride to aldehyde is also converted by this reagent. So here, if we will see the mechanism, what will happen? Here you can see that this reducing agent will give the hydride ion to this carbonyl carbon atom. After attack of nucleophilic attack of this hydride ion, here the carbon oxygen pi bond will break, and we will get the O minus here, O minus ion. Then this O minus will push the lone pair of electron to here, to this direction, this carbon atom, and this chlorine group will be knocked out. It will leave the elimination of this halide group will takes place to give the corresponding aldehyde. So this is the mechanism of this reaction. So here this is not ketone. You consider here any halogen group. Yeah, maybe some mistake is there. Okay. So this is the mechanism for this type of reaction. Now we have discussed the reduction of amide with lithium aluminium hydride. So what was the reduction procedure? What will happen first? As we can see here, this lithium aluminium hydride will attack on this carbonyl carbon atom. The hydride ion of this reagent will give a nucleophilic attack. By nucleophilic attack will give a O minus ion generation, and this is the addition of hydride ion. So after getting this intermediate with O minus ion, O minus will attack on aluminium carbon atom. It will attack on aluminium carbon atom to give this intermediate with oxygen substituted by AlS3. Substituted AlS3. Now after getting this intermediate, what will happen? This nitrogen will push this its lone pair of electron here, and it will cleave the oxygen carbon bond. It will give a cleaving for the oxygen carbon bond to give the iminium ion intermediate. After getting the iminium ion intermediate, This iminium ion will be attacked by the again lithium aluminum hydride will attack on this iminium ion as a nucleophile to give the corresponding amine. So we will get the amine after hydride attack of the nucleophile. We will get the amine formation. So this is the mechanism for this reaction. Okay. So the formation of amine will takes place from amide to amine. So lithium aluminum hydride will reduce the amide to amine. Okay. Now this is the last example, last question. So in this question we have discussed that the first BH3 will attack on this double bond by Markovnikov of rule reaction. Markovnikov of rule. According to the Markovnikov of rule, the most electronegative atom will attack on more substituted carbon atom. So according to electronegativity, so if we will discuss about the boron and hydrogen electronegativity, so hydrogen have the highest electronegativity compared to the boron. Boron is more electropositive, so the more electronegative atom will always attack on the more substituted carbon atom. So that's why hydrogen will be attacked over here, and BH2 group will be attacked by this carbon atom. This carbon atom. Here hydrogen will act as a nucleophile, hydride ion, nucleophile, and BH2 is a electrophile, or plus sign will be here, and it will be attacked by the second carbon. So this is a Markovnikov addition. By Markovnikov addition, we will get this intermediate. After getting this intermediate, the peroxide will attack from the opposite side of the BH2 group to give the corresponding alcohol. So the mechanism for this reaction is here. After getting the BH2, sodium hydroxide and hydrogen peroxide will attack will be created by this intermediate. So what will happen first? This hydrogen peroxide will be created with NaOH to give the corresponding water and sodium peroxide here, sodium peroxide, or we can say a deprotonated peroxide. As deprotonated peroxide is more nucleophilic compared to the neutral peroxide, and the base is also used for the speeding the rate of reaction. So base is used for speeding the reaction here, and yeah, and we will get this intermediate. This intermediate, then this intermediate will attack on this boron atom to give a to give a boron oxygen bond formation. After boron oxygen bond formation, uh, this oxygen oxygen bond is very weak. Because of this weak bond, this cleavage of this bond is taking place here. After cleaving the oxygen oxygen bond, rearrangement will take place to give a corresponding intermediate, which is rearrange intermediate. Here you can see that the carbon oxygen bond formation is taking place here to here, and this bond is breaking here. Then after formation of this intermediate, again this hydroxy group OH minus will attack on boron atom, and this boron oxygen bond cleavage will takes place here. After boron oxygen bond breaking, here we will get O minus ion generation, which is stabilized by the sodium ion, and then this O minus will be created with a water, which will abstract the proton from the water to give the corresponding alcohol. So alkoxide removes the proton from water to generate a neutral alcohol. This is our alkoxide. Yeah, this is our alkoxide. which is abstract the proton from water to give a neutral alcohol. So this is the mechanism for this reaction. I hope all of you are clear with this mechanism. So any doubt, any question, or any difficulty regarding these questions is there, you can ask me in next lecture, or these slides will and lecture will be available on YouTube. You can watch over there and you can ask me any question there also. Thank you so much for your time.